Hello, and welcome to our introduction to our next unit, which is all about sampling distributions. So let's go ahead and get started. I want to start by reviewing some important symbols, more symbols than vocabulary, because they will become increasingly important this unit and into the rest of the semester. So what we're reviewing is our symbols for a parameter versus a statistic. Remember, a parameter is something that is true for the population, and then a statistic is something that is true for a sample, right? And then I had this little table. This was way back from the beginning of the year that showed what symbols we use for what. So for means, which is when we have numerical data, so we'd find the average of that number of those numbers, we use the symbols mu and x bar. Mu is when it's a mean for the entire population. X bar is when it's the mean for the sample. And then for proportions, which is when we're dealing with categorical data, we'll find the proportion of people who said certain things. We use p and p hat. P is the symbol we use when that proportion is for the entire population. P hat is the proportion for the sample. So those are going to become, like I said, more and more important this semester. So I wanted to remind you of them. Make a little note of them. Write them down again in your notes if you need to so that you don't forget what is what. So let's talk about sampling distributions, what they are, why they're important, and we'll give you some examples of sampling distributions. So a sampling distribution, it's not a sample distribution, and as we get into some of our further lessons, we'll kind of explain the difference between what those are. But a sampling distribution is a collection of a large number of sample statistics, either means or proportions, of a given sample size. So let me demonstrate what I mean by that with a little bit of an example. So in my classroom, I have this thing I call a sampling bowl. It looks kind of like this. It's just a big glass, or it's actually plastic, but clear bowl that has a bunch of beads in it. Some of the beads are white and some of the beads are red. And then we have these little kind of paddle things with divots in them that we can use to take samples. If you were in my classroom like normal this year, you would have seen this off to the side of the room on a table, and you would have been wondering all year, what is that thing? What do we use it for? You may have even asked me a couple times. And today would have been the day that you would find out what it is and what we use it for. But alas, most of you have not been in my classroom this year, so you didn't have that suspense of confusion of what it is, but there you go. So it's a big bowl, and our goal with this is to kind of determine or try to figure out what percent or what proportion of the beads in the bowl are red. Right, so we can look at it and guess. You can kind of correlate this or imagine this to a real life circumstance, something more important than beads in a bowl, but you might be interested in a large population. What proportion of them wear glasses, or what proportion of people in our population eat pancakes for breakfast, whatever you want to do. So we're trying to estimate something that's true for a population, but maybe it's too cumbersome. There's too much going on. So we take samples, and a sampling distribution is all about what do those samples typically look like. So what we would have done in class, I made a little GIF for us. I would take this little paddle. Can't tell in this picture. There's me sitting my little sample still. I would take this little paddle and kind of dip it into the beads and shake it off, and then we would get a sample, pretty random sample, of beads that are fitting into these little kind of divots in that little paddle. And from that sample, we can figure out what is the proportion of the sample that are red. Okay, and if I do this repeated times, which in past years with my students, I have each of them take a sample or two or three, and we create the sampling distribution. So this is a graph. I had my students write p hat to represent their sample proportion, just to drive home the point that p hat is the symbol we use for a sample proportion or a sample statistic. But we have these collection of sample statistics from all of my students, and we can kind of see the patterns start to emerge. I can see what sample proportions were the most common. It was right here, kind of just below 0.25, which was about 6 red beads. And then we can see like how spread out the values are. And we went down as far as just below 0.05 and up to almost 0.45 in terms of how spread out they were. So that is a sampling distribution. It's a collection of a large number of sample proportions. That was with a sample size of 25. So each of these samples were taken with a sample size of 25. So I then went ahead and started collecting, what if we took bigger samples? So I have a bigger paddle that's got 100 little divots in it. And we take a sample, kind of the same way. You dip it in there, shake it around, make sure all the little beads fall into the little spots. And again, we count what proportion of the beads in those little spots are red. And we do that repeated numbers of times. All of my students did it. And again, we came up with this sampling distribution, a collection of sample statistics in terms of what proportion of each sample are red. So same idea, but these are all sample sizes of 100. So let's clean those graphs up a little bit. So I made some graphs using that same data with the computer. So here's our graph, our histogram with sample sizes of 25, right? So I can see that my most common answer was right here just below 0.25, right? But we can kind of see how spread out it is. We can talk about the shape of this graph. It looks kind of skewed to the right, but fairly unimodal, etc. Then we can look at our graph, our histogram for sample sizes of 100, which is much more compact. It's closer together. My tallest bar is in this kind of 0.2 region, but everything's a lot closer together. So my smallest value is much higher than the one for sample size of 25. My largest value is a little smaller. It's still a little skewed to the right, but definitely going more towards what we would call symmetric and unimodal or normal. It's not perfect, but it's getting there. So from these sampling distributions, I can not only guess by looking at this what the true proportion of red beads in the bowl might be, I'm also getting an idea of how spread out these sample proportions are, right? So just so you know, the sampling bowl actually has about 21% red beads. So I can see that reflected in both graphs, right? It's not perfect because these were, real life samples. We don't always get a truly random sample, but definitely pretty close. But the big thing I wanted my students to notice, and what I want you to notice here, is not only how we can estimate what's the true proportion or the true center of the graph, but we can also talk about the difference in how spread out our values are. So our sample statistics, when we had a smaller sample size, were a lot more spread out, right? Whereas in terms of proportions, whereas with a sample size of 100, we were a lot more compact in our guesses. So we're getting kind of two ideas. What is the actual true proportion? But then also how varied are these possible answers? So a sampling distribution is important because it gives us an idea of what is typical for a sample of a certain size taken from a certain population, right? In this example, I can kind of see what's typical or what's normal or whatever of a sample size of 25 and a sample size of 100. And that helps us decide whether a sample statistic that we get is statistically significantly higher or lower than we would expect. And it kind of helps us decide whether things are reasonable. So for example, if I told you I took a sample of size 25 from the sampling bowl, the same one, didn't change anything, and I got 80% red beads. Is it possible that dipping in there would give me 80% red beads? I mean, sure, it's possible, but I can tell from my graph that that's not very likely. So I would question a couple of things here, right? I would say either I'm really, 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 really lucky, or, because this is where 0.8 would be, or one of my other earlier assumptions is off. So maybe it's not the same sampling bowl. Maybe this is a sampling bowl with higher reds. Maybe I didn't actually take a random sample. Maybe I handpicked red beads to put in the little paddle to get my answer. But this sampling distribution is giving us that idea of what to expect, right? Versus what I say I got. And I can help decide, is that statistically probable, or am I questioning that sample proportion that I'm saying that I got? If I said I got a proportion of 0.4, again, not super likely, but it's happened. So maybe I'm not as questioning on that one. But that is what a sampling distribution does for us. It tells us what we can expect from a sample of a certain size, which helps us decide whether certain stated hypothesized values are likely, or are they completely out of nowhere? Because we can compare it to what is typical for a sample of that size from the population. I'm going to go through a couple of things that we kind of noticed and just put it in more context. So what we notice about the sampling sizes for our sampling models or sampling distributions for smaller sample sizes versus larger sample sizes. is that there was a big difference in spread. Shape kind of depends on a couple factors that we'll talk about next time, but the biggest thing is I want you to see that difference in spread. So the smaller sample size, the sample statistics, the sample proportions were much more spread out, versus the bigger sample size, we had much more compact and close together proportions. So as our sample size increases in a sampling distribution, spread should decrease and vice versa. So as sample size increases, your spread for that sampling distribution is going to decrease. So the big idea is that your sample size is going to affect the variability, but it's not really going to affect the center. We saw that both of our sample sizes kind of did a fairly decent job of estimating the true proportion of red beads in the bowl, about 21%. It wasn't exactly perfect, but they were both kind of in that general area. So the center of the graph was not affected by sample size, but what was different was the amount of variability, how spread out the graphs were. The other thing I wanted to mention in terms of all of this, just something to keep in mind, we talked about bias a lot at the beginning of the year and how bias affects samples. This is just one example of bias. This is an example of bias more in the wording of a question, but we can also have bias in the way that we take a sample. But either way, if there's bias in our sample or in our sampling method, that's going to affect our sampling distribution as well. So if we sample properly, the center of our histogram for our sample statistics histogram, our sampling distribution, should be right at where that population parameter, the true thing, actually is. So it's right at the center, and we can use that sampling distribution as a good estimate for what is true about the population. But if there's bias in our sampling method, or even just in the way that we ask the questions in our survey, we end up with a bias estimator, which basically means we get answers, we get sample statistics that are way off from where the true population parameter actually is. Maybe it's way above, maybe it's way below, but it's off from what it should be, right? So our sampling model, our sampling distribution doesn't properly estimate what's true about our population. And that's not something we're necessarily going to know. Like, we don't know generally when we take a sample what the true population is. But if we're doing something that's biased, we know it's going to be off. So the big idea there is that bias affects center. It's going to cause my center to be off, but it doesn't really affect variability necessarily. So bias affects where the center of the graph is and whether the center is properly estimating what's true about the population, whereas sample size affects how spread out your sampling distribution is in terms of the variability. So those are our couple of things to keep in mind. As this introduction to sampling distributions, we will get more into specifically sampling distributions with proportions, and then we'll talk about sampling distributions with means or numerical data, and look at kind of how they're similar, how they're different, and what things that we can do with that information. So that is it for now. Hope you have a good rest of your day and weekend and whatever, and I will see you guys next time.